The next humidity measurement device is what's called a chilled mirror hygrometer. And just as the name suggests, inside such an instrument, there is a little mirror that reflects light. This mirror is electronically cooled. And by looking for a change in its reflective properties, we can determine where dew first forms. And by measuring that temperature, we know the dew point of the air or the gas that's going across the mirror. Now, one can get very high accuracy measurements with a dew point hygrometer, but they do have maintenance issues associated with them. In order to obtain a relative humidity value from a dew point hygrometer, one first must know, is the mirror covered with dew or is it covered with frost? And this brings a very common question, and that is, at what temperature does water freeze? Well, I used to think it was 0C, 32F. The true answer is water freezes at any temperature it feels like it. It will often supercool. It's not uncommon to see liquid water present at minus 30 degrees C on a chilled mirror hygrometer, particularly when things are clean and pure. Now, this uncertainty of dew versus frost can lead to significant humidity errors. Looking at the table here, we can see if we have 25 degrees C and 10% relative humidity, if there's dew forming on the mirror, it will be at minus 8.7 C. But if it's frost, it's minus 7.7 C. Now, if the temperature was 15 C and the humidity was 15%, again, you can see substantially different temperatures of the mirror if it's dew or if it's frost. And at 10 degrees C and 20%, it's just that much different. Well, the problem is you may not know if it's dew or frost. And if you don't know, we can see this dew-frost error can be quite significant. At 25 C and 10%, as we can see in the table, you can have an error or an uncertainty just from the dew-frost of 0.8% RH. And that goes up to 2.2% when it's at 10 degrees C and 20% RH. So although we have very accurate capabilities, unless we know the dew or frost state on the mirror, the introduced errors can be quite significant. So this is something one must take into account when using a chilled mirror hygrometer. So let's talk about capacitance for a moment. If we go back to high school science, we might remember that a capacitor is simply two conductive plates, called electrodes, separated by a space or an insulator. This capacitor has the ability to store electric charge. Now, the amount of electric charge that is stored is proportional to what's called the dielectric constant. And this is a physical property of the insulator. Air has a dielectric constant of 1, and water is considerably higher than that. It just allows greater storage of electrical charge. Now, if we were to take this capacitor and make the conductive plates porous in such a way that water vapor could pass through them, it would allow water vapor to be stored in this dielectric, or in this case, the dielectric or insulator is a polymer. So we have conductive plates, and the water vapor can pass freely in and out of the dielectric polymer. Well, when we have increasing relative humidity, we can expect more water molecules to enter and fill this dielectric polymer. This will increase the electrical capacitance. Conversely, if the humidity becomes lower in the environment, water vapor will escape from the dielectric polymer, and that will decrease the electrical capacitance. This change in electrical capacitance can be measured, and it is proportional to the relative humidity. Now, the change in electrical capacitance is not that large, so it does put a challenge on a measuring system to accurately resolve and repeatably measure this change. Well, what can go wrong with a system like this? Well, drift or measurement errors can be caused by surface contamination or internal contamination. And as we said earlier, the humidity sensor internal structure is exposed to the environment, so it is subjected to contamination from the environment. Well, surface contamination actually alters the relative humidity near and on the sensor itself. So although the sensor may be measuring accurately, the environment that it sees right around it is actually not a true representation of the greater humidity environment, causing an improper reading. Sometimes contamination can be directly on the sensor, or sometimes it can even be near it or on its enclosure or probe body. Salts are a common source of this problem, and an impure water source may be the source of them. This can occur with ultrasonic stability chambers, for example, when the water is splashed, if you will, around the chamber and onto the sensor, causing an error in the measurement. Let's look at a real-world example of what can happen when we have surface contamination. This is a case where a measuring device underwent a single-point calibration at around 75% RH. Now, as we can see from its results, it actually looks pretty good. It's pretty close to being at 75% in every regard. And as we can see, it actually looks pretty good. At or near 75%, which is the actual RH shown on the bottom of the graph, we can see that the corresponding measured value is actually pretty close. So everything looks fine. But if that same sensor were calibrated over a very wide range, we'd see quite a different picture. Again, the actual RH is shown along the bottom with the measured RH along the side. Now, again, it looks great at 75%, but if we were to change higher humidity or lower humidity, the values are quite inaccurate. And the problem here could be that if the measured system, which may be operating at 75%, goes out of specification, let's say it's a chamber that drops to 70% or 80%, well, the problem is we may not get an alarm because the true change in humidity is not being measured. Now, internal contamination occurs when various chemicals or contaminants have actually entered the dielectric or the polymer of the humidity sensor. These could be cleaners or volatile organic compounds, for example. Now, this contamination interferes with the absorption and diffusion of the water vapor within the sensor, and it shifts the RH readings, sometimes by quite a significant amount. Sometimes this can be reversible by heating up the humidity and essentially boiling off the contaminant, but usually it doesn't reverse, at least not totally, because the polymer has been damaged or altered in some physical way. We'll talk about another characteristics of most RH measurement systems, particularly capacitive RH measuring systems, and this is hysteresis. This is not really a drift, but it's still a very significant source of RH measurement error. Hysteresis is when a measurement does not return to an original value after a large excursion. Water molecules are effectively trapped within the dielectric. Often it's reversible, at least partially, but it may take a substantial period of time, sometimes days, to recover. Heating the RH sensor can actually help reverse much quicker. In this particular example, we see an RH measurement device was at a relatively low or dry relative humidity value. It then was exposed to a much higher humidity level for an extended period of time, and then brought back down to that lower or drier environment. Well, hysteresis occurs when the humidity measurement device does not return completely to that low value. That difference, delta RH, is shown on this graph, is the hysteresis value of the non-return value when brought back to the initial low humidity point. Now, this offset can, in some sensors, be quite small, but in other sensors, and again, depending on the magnitude of the humidity and the length of the exposure can be several % RH. It can be quite significant.